Okay, so picking up where we left off before, we talked about what it means to have a vector in component form. And oftentimes we don't have the vector to look at right away. So in the previous video, we looked at a picture that had several of the same vector, in multiple locations throughout the plane. And we were able to draw a little right triangle to determine what the horizontal and vertical components of that vector were. But what if we're only given a description of a vector in terms of its initial and terminal point? How do we come up with the component form for a vector in that case? Well, suppose you have a vector whose initial point is p x1, y1, and its terminal point is q with coordinates x2, y2. It's fairly easy to see that if you draw this little right triangle right here, the length of the base of this right triangle is going to be the difference between these x coordinates here, x2 minus x1. Similarly, y2 minus y1 should give me my vertical component. And that gives me a formula that I can use for calculating the component form of a vector if I know its initial and terminal points. If the vector is in 3 space, unlike 2 space, which is this case, then it's the result is pretty similar. So if I want to find the component form of a vector with initial point p, terminal point q, then I simply subtract the coordinates of my terminal point minus the coordinates of my initial point to get each component for that vector. One thing I want to mention here, we're going to be covering a lot of material, like a lot of the basics concerning vectors, and I'm waiting until kind of closer to the end of the lecture to do some examples, because I'm going to combine a lot of these things in a single example. So that's why we're kind of rushing through and hitting these other topics without practicing them right now, because we're going to do that a little bit later. Okay, so this is an important formula determining the component form of a vector given its initial and terminal points. What's something else we might need to do with a vector? Well, we've mentioned its magnitude before, and it would be helpful if we could use the component form of a vector to compute the magnitude of that vector. Now, a simple way of doing that is if we come back here, that's the wrong one. If we come back here and we look at, for example, this vector A. If we take a vector and we put it, if we place it as a position vector, then the magnitude of that vector is the same thing as the distance from the origin to this point here, A1, A2, A3. However, the coordinates of this point are the same as the components of that vector. So we can apply distance formula to come up with the magnitude of a vector by thinking of it in that way. And that leads to these two formulas. The notation that we're going to use for the magnitude of a vector is the absolute value, vertical bars. And we need to be careful about that because, as we're going to see a little bit later, sometimes a single problem may involve both the absolute value of a real number and the magnitude of a vector. And those two notations look the same, but they mean different things. So usually we have to be careful and make sure we're understanding the context of a problem and what kind of quantities we're looking at to make sure we're knowing how to interpret that. But anyways, the magnitude of a vector A in 2 space with components A1 and A2 is shown here. Square root of A1 squared plus A2 squared. Just comes straight out of our distance formula. If the vector is in 3 space and has components A1, A2, and A3, we get a similar looking formula shown here. So we're going to use that to compute magnitudes of vectors, which we do a lot of in this class. Okay? Now, down here, we've discussed how to add, subtract, and multiply vectors, how to add and subtract vectors and how to multiply vectors by scalars, but we did that all in the geometric context. We just looked at how it affected those arrow representations of vectors. But what if we're working with vectors in component form? How does addition, subtraction, and scalar multiplication work? Well, fortunately, it works in about the most intuitive and simple way that you can imagine. So here, if A has components A1, A2, and B has components B1, B2, if I want to find the sum of A and B, then I'm just adding their first components and adding their second components, and that gives me the new components for that resultant vector. Similar thing for subtraction, and we call this component-wise addition, component-wise subtraction. Scalar multiplication also uses component-wise multiplication. If I have vector A and I want to multiply it by the scalar C, that's the same thing as multiplying each component by C individually. You can see this worked out down here. Why do they work that way? It's not just for convenience. Remember, we've already defined addition, subtraction, and scalar multiplication in the context of those arrows. Geometrically, what do those operations mean? If I'm going to go and say that addition, subtraction, and scalar multiplication work this way in component form, this better not mess up what we already said addition, subtraction, and multiplication by a scalar is supposed to represent. So we need to make sure that this way of computing or way of performing operations on vectors is consistent with the way we've already defined those operations. So taking a look at addition, here's an example of addition. If I wanted to add vector A to vector B, you can see the sum A plus B right here in that tip to tail method. But now let's take the vectors A and B and break them down into their components. So A, you can see where A1 and A2 make up the horizontal and vertical component of that vector. Now with B, B1, its horizontal component would be here, B2, vertical component, that would be here. And notice this right triangle is not sitting on an axis the way that this one is. So I could kind of create a little rectangle here, making this side the same as B1. This side here would be the same as A2. And look at what we have. This larger right triangle makes up the components of my sum, A plus B. And I can see that the horizontal component really is the sum of the horizontal components of A and B. The vertical component really is the sum of the vertical components of A and B. So that jives with our way of working with addition in component form up here. Scalar multiplication, why does that work the way that we have it written up here? Well, again, if you have a vector A and you create that right triangle to show where its components are, A1 and A2, if I were to multiply A by a scalar, the effect that it has on this this right triangle is that it scales it by the same amount that we scaled A by. You can think of this as either zooming in or zooming out, or enlarging or shrinking this right triangle. But we know from geometry that if you zoom in or zoom out on a triangle, then the two triangles that we have here for comparison are similar, and that means that their side lengths are proportional. A consequence of that is that if you multiply one side by some scalar c, then the other sides would have to also be multiplied by that same scalar so that we have that similar triangle. And here we see that A1 and A2, the components of A, had to be multiplied by C to give us the components of CA. That's exactly what's happening here. Okay, so this is consistent with how we defined those operations before. Okay. One thing, just a brief mention here. In Calculus 3, we're almost exclusively focusing on vectors in 2-space and 3-space. And that's because we can visualize those. And most, applications in kind of basic physics and stuff like that would require the use of vectors in 2-space or 3-space. However, if you think of a vector as just its components, there's no reason why we have to restrict vectors to having only 2 or 3 components. You can give a vector as many components as you want. And in that sense, we can talk about vectors as living in higher dimensions. An n-dimensional vector, for example, would look like this, something with n components. Now, that may seem a little bizarre that we would do that, but the key here is that vectors don't have to be thought of spatially. It just so happens that vectors with 2 components or 3 components have a very convenient and easy representation in 2 or 3-dimensional space, which we can visualize. 4, 5, 6-dimensional space, 100-dimensional space, all of those things exist. We just can't visualize them. But we can describe them in terms of vectors with however many components we would require for something like that. So this is just to say that these things do exist and they are useful. We just don't really mess with them much in this class. All right, let's talk about some properties of vectors. I'm not going to go through this one by one, but this is basically to establish some properties of arithmetic when working with vectors. Don't worry about this symbol right here, Vn. This is just a symbol that the author is using for the set of all vectors in n-dimensional space, and then he kind of abandons that notation later, so don't worry about that. Just think of A and B as any vectors, either in 2 space or 3 space or n space. Vectors have a lot of the same properties that real numbers have. We talked about how vector addition is commutative. A plus B and B plus A are the same vector. Adding a 0 vector to a vector A is going to be, it's not going to change A. And if you think about why that would be the case, what is the component form of the 0 vector? Well, we didn't talk about that, but it would have, all of its components would have to be equal to 0. And if you think about that for a moment, it should make sense why that's the case. Similarly, adding A to its opposite gives us the 0 vector, kind of like how x plus negative x is equal to 0 when x is a real number. And we have, variations on the distributive property. This is a property called homogeneity. Multiplying a vector by the scalar 1 gives us the same vector. All of these are familiar properties, and we're just used to thinking of them in real numbers. This is to show that they also work with vectors. Okay. Now I'm actually going to skip past this proof. I'm going to let you read this if you like. This is a proof of the 5th property right here that I wrote out, multiplying a scalar times a sum of 2 vectors. It's basically just saying let A and B be n-dimensional vectors, and here's their component forms, and then showing that using those component operations that we talked about, that you can show that C times A plus B is equal to CA plus CB. But that, you go ahead and read through that, make sure it makes sense to you. It's kind of messy to go through. Moving along, in 2 space and 3 space, there are specific sets of vectors that serve a really useful purpose, and we use them throughout the course. They're called standard basis vectors, and we assign them special symbols. So in 2 space, whenever you see a lowercase bold I, we're talking about this vector specifically, the vector 1, 0. That's its component form. J is the vector 0, 1. Okay? If we know that we're in 3 space, I and J represent different vectors. I is 1, 0, 0, J is 0, 1, 0, K is 0, 0, 1. Here's where those vectors live when you put them as position vectors in 2 space or 3 space. You can see that all of them coincide with axes. Not only that, each one of them has a length or a magnitude of 1, which you can find by using that formula for calculating the magnitude on any of these vectors here. Okay? So those serve a special purpose, and we're gonna encounter them throughout the course, like I said. What do I have a blank page in here? Oh, okay, an extra page in there for some reason. So one thing that's important to know how to do is how to take a vector that's in component form and write it in terms of those standard basis vectors. If this were a linear algebra class, we'd be describing this representation as a linear combination. We're not really going to use that term much in this class, though, so you don't need to know that. So let's think about this for a moment. If A, the vector A, has components A1, A2, and A3, I could blow this thing up into a sum of 3 vectors. A1, 0, 0, plus 0, A2, 0, plus 0, 0, A3. You can see that if you added component-wise, this would come out to this. Okay? And then I can factor the A1 out, A2, A3, and so on, as a scalar, and represent all 3 of these vectors as a scalar times one of my standard basis vectors. You notice that's I, J, and K right there, so I can write that as A1I plus A2J plus A3K. Okay? So basically what that means is if I have a standard basis, or if I have a, what do you call it, a vector in component form, I can write it in terms of the standard basis vectors by using those same exact components as the coefficients on those things. So an example would be something like this. If I have the vector 2, 1, 9, that's the same thing as 2i, and I want to mention something about how I'm writing these right now, plus j plus 9k. Couple of things I want to mention about this. Notice that I put these little arrows over I, j, and k when you're not really seeing them here. The reason I'm doing that is because I, j, and k are vectors, and when I'm typing things, vectors are going to appear in bold. But I don't really have an effective way of doing bold when I'm handwriting these things. So this is a common alternative that you'll see me use a lot. Because I can't really write in pen in a way that makes these bold without making it kind of messy, I can use these arrowheads to show that these things are vectors. Okay. The other thing I want to mention is that you notice the 1 is not appearing explicitly here, and that's because 1 times j is just j, so I don't really need the 1. But these two things are the same. All right. One more thing here. So we're going to be working a lot with these things called unit vectors throughout the course. A unit, the word unit in math means 1. That's how we interpret that. So a unit vector then is a vector that has a magnitude of 1. And oftentimes when we're working with vectors, we need, as a preliminary step in a problem, we need to find a unit vector that has the same direction as some given vector, say u. Okay, u can have any magnitude, but the goal is to find a vector that's parallel to this one, has the same direction specifically, but only has a magnitude of 1. How do we do that? Well, one thing I do know from what we talked about with scalar multiplication is that if you multiply a vector by a scalar, specifically a positive scalar, it doesn't change the direction of that vector. It only scales it. So it seems to make sense that if I can find the right scalar to multiply u by, it will shrink u or expand u to a vector that has a length of 1 but never actually changes its direction. And that's what we're looking for. So we're gonna show how to find that scalar, but an important property that we're going to use is this one. Suppose you have a scalar times a vector, c times u, and you want the magnitude of that vector. If you use that formula that we came up with a while back for finding the magnitude of a vector, you can prove without much trouble that this is equal to the absolute value of c times the magnitude of u. Now this is something that I had warned you about previously. I'm using two sets of what look like absolute value symbols, but they each mean something different. Because the thing inside here is a scalar, this is talking about the absolute value of that scalar. And because the thing in here is a vector, those vertical bars mean the magnitude of that vector. They're not the same concept, but the symbols look the same. So you have to be careful. All right. Now, let's suppose that k is a positive number, and it's that scalar that we're looking for that we can multiply to u to create a unit vector in the same direction as u. Well, if that's the case, then that means that the vector ku should have a magnitude of 1. But when I write this, the magnitude of ku, using this property up here, that's the same thing as the absolute value of k times the magnitude of u. But again, we assumed k was positive to begin with, so the absolute value of k is really just k. So k times the magnitude of u should equal 1. If I solved this for k, then I get k equals 1 divided by the magnitude of u. That's that magical scalar that we need in order to get a unit vector in the direction of some specific vector u. So that's summarized here. If we need to find the unit vector in the direction of u, that's equal to 1 over the magnitude of u times the vector u. Now, even though we've never talked about an operation called scalar division, we use this notation as shorthand for this. So this looks like it says u divided by the magnitude of u, but that's dividing a vector by a scalar, and we haven't defined an operation like that. We interpret this to mean this, okay? Finally, we get into some examples. So let's go through these here. Notice I have 3 points, P, Q, and R, and the coordinates are shown here. All 3 of these points are in 3 space, and I want to use these points to create a couple of vectors. Vector U is going to be the vector with initial point P and terminal point Q, and we're asked to do a couple of things here. I need the component form of both of these, and I need the magnitude of both of those. So starting with U, remember, the component form of a vector is obtained by taking the coordinates of its terminal points and subtracting the corresponding coordinates of the initial point. So, for example, -2 minus 1. -2 minus 1. 1 minus 0. -2 minus 4. Which in component form gives me -3, 1, -6. Okay? V, we handle that in a similar way. This time, V it's got its initial point at Q and its terminal point at R. So I do the coordinates of R minus the coordinates of Q. -4 minus -2. Okay? -4 minus -2. Then I have 0 minus 1. And then I have 1 minus -2. 1 minus -2. Okay, that's going to be -2, -1, 3. Okay, so there's the component forms for those vectors. The next thing I need are the magnitudes of those vectors. And now that I know the component forms, that's easy to do. What's the component, or what's the magnitude of U? Well, remember, we have this formula. It's equal to the square root of the sum of the squares of its components. -3 squared plus 1 squared plus -6 squared. Okay, so that's 9 plus 1, that's 10, plus 36, so that's 46, root 46. I'm not going to worry about simplifying that radical right now. I'm just going to leave it like that. What about the magnitude of V? Same idea. Square root of the sum of the squares of its components. -1 squared plus 3 squared. So that's 4 plus 1, that's 5, plus 9, that would be 14. So I get the square root of 14 as my answer there. Okay? So we got the component forms, we got the magnitudes. We've used a couple of the formulas that we've talked about. Pretty straightforward. It's just knowing how to use those things. Next thing I want to do, evaluate 5u minus 2v. So this is a combination of scalar multiplication with my vectors as well as vector subtraction. What does this look like? Well, let me rewrite this with u and v in component form. U is -3, 1, -6. Minus 2, where did that go? Component form for V is -2, -1, 3. Okay? I'm going to multiply these scalars in. So 5 times -3 is -15, and a -5, and a -30 right here. I'm going to just leave the minus there, but multiply the 2 in. So I get -4. 2 times -1 is -2, and then I get a 6 here. Okay, so I deal with the scalar multiplication first. And now I can subtract component-wise. What is -15 minus -4? That's -11. What's 5 minus -2? 7. What's -30 minus 6? -36. There it is. Okay, fairly straightforward. How do we do part C? I want to find the unit vector in the direction of V. We just talked about this, came up with a formula for it. The first thing you need to do is find the magnitude of V. But fortunately for us, we've already done that. So the unit vector in the direction of V will be, remember, it's V over the magnitude of V. But that's the same thing as 1 over the magnitude of V times V. What is the magnitude of V? Up here we found that it was root 14. I have 1 over root 14, and V in component form looks like -2, -1, 3. Multiplying that in, I got negative 2 over root 14, negative 1 over root 14, and 3 over root 14. In this class, you really don't need to rationalize denominators. It's preferable to leave radicals and denominators if they appear there, because there is absolutely no good reason to be doing that in this class. If my trigonometry students, I make them rationalize because there's some patterns that are apparent when you're learning the unit circle if you rationalize denominators. But outside of that, there's really not much purpose behind it. So go ahead and leave radicals in your denominators. It's not going to hurt you. Okay? We have a couple more examples to do, which we're going to do in the next video.